In mathematics, a permutation group is a group G whose elements are permutations of a given set M and whose group operation is the composition of permutations in G. The group of all permutations of a set M is the symmetric group of M, often written as sim. The term permutation group thus means a subgroup of the symmetric group. If M equals 1, 2, n, then sim of the symmetric group on n letters is usually denoted by Sn. The way in which the elements of a permutation group permute the elements of the set is called its group action. Group actions have applications in the study of symmetries, combinatorics and many other branches of mathematics, physics and chemistry. Basic properties and terminology. Being a subgroup of a symmetric group, all that is necessary for a set of permutations to satisfy the group axioms and be a permutation group is that it contain the identity permutation, the inverse permutation of each permutation it contains, and be closed under composition of its permutations. A general property of finite groups implies that a finite non-empty subset of a symmetric group is again a group if and only if it is closed under the group operation. The degree of a group of permutations of a finite set is the number of elements in the set. The order of a group is the number of elements in the group. By Lagrange's theorem, the order of any finite permutation group of degree n must divide n. Notation. Since permutations are bijections of a set, they can be represented by Cauchy's two-line notation. This notation lists each of the elements of M in the first row, and for each element, its image under the permutation below it in the second row. If is a permutation of the set, then, for instance, a particular permutation of the set 1, 2, 3, 4, 5 can be written as. This means that sigma satisfies sigma equals 2, sigma equals 5, sigma equals 4, sigma equals 3, and sigma equals 1. The elements of M need not appear in any special order in the first row. This permutation could also be written as. Permutations are also often written in cyclic notation so that given the set M equals 1, 2, 3, 4, a permutation G of M with G equals 2, G equals 4, G equals 1 and G equals 3 will be written as, or more commonly, since 3 is left unchanged, if the objects are denoted by single letters or digits. Commas and spaces can also be dispensed with, and we have a notation such as the permutation written above in two-line notation would be written in cyclic notation as composition of permutations. The group product. The product of two permutations is defined as their composition as functions. In other words, sigma pi is the function that maps any element x of the set to sigma. Note that the rightmost permutation is applied to the argument first because of the way function application is written. Some authors prefer the leftmost factor acting first, but to that end permutations must be written to the right of their argument, often as an exponent, so the permutation sigma acting on the element x results in the image x sigma. With this convention, the product is given by x sigma pi equals pi. However, this gives a different rule for multiplying permutations. This convention is commonly used in the permutation group literature, but this article uses the convention where the rightmost permutation is applied first. Since the composition of two bijections always gives another bijection, the product of two permutations is again a permutation. In two-line notation, the product of two permutations is obtained by rearranging the columns of the second permutation so that its first row is identical with the second row of the first permutation. The product can then be written as the first row of the first permutation over the second row of the modified second permutation. For example, given the permutations, the product QP is the composition of permutations, when they are written in cyclic form, is obtained by juxtaposing the two permutations and then simplifying to a disjoint cycle form if desired. Thus, in cyclic notation the above product would be given by. Since function composition is associative, so is the product operation on permutations. rho equals sigma. Therefore, products of two or more permutations are usually written without adding parentheses to express grouping. They are also usually written without a dot or other sign to indicate multiplication, neutral element, and inverses. The identity permutation, which maps every element of the set to itself, is the neutral element for this product. In two-line notation, the identity is in cyclic notation, E equals, which by convention is also denoted by just or even equals. Y1 also has sigma minus 1 equals x. In two-line notation, the inverse can be obtained by interchanging the two lines. For instance, to obtain the inverse of a single cycle, we reverse the order of its elements. Thus, to obtain the inverse of a product of cycles, we first reverse the order of the cycles, and then we take the inverse of each as above. Thus, having an associative product, an identity element, and inverses for all its elements, makes the set of all permutations of M into a group. A permutation group. Examples. Consider the following set G1 of permutations of the set M equals 1, 2, 3, 4. E equals. This is the identity, the trivial permutation which fixes each element. A equals. This permutation interchanges 1 and 2, and fixes 3 and 4. B equals like the previous one, but exchanging 3 and 4, and fixing the others. AB equals. This permutation, which is the composition of the previous two, exchanges simultaneously 1 with 2, and 3 with 4. G1 forms a group, since AA equals BB equals E, bar equals AB, and ABAB equals E. This permutation group is isomorphic, as an abstract group, to the Klein group phi-4. As another example, consider the group of symmetries of a square. Let the vertices of a square be labeled 1, 2, 3 and 4. The symmetries are determined by the images of the vertices, that can, in turn, be described by permutations. The rotation by 90 degrees about the center of the square is described by the permutation. The 180 degrees and 270 degrees rotations are given by M, respectively. The reflection about the horizontal line through the center is given by N. The corresponding vertical line reflection is. The reflection about the 1, 3 minus diagonal line is, and reflection about the 2, 4 minus diagonal is. The only remaining symmetry is the identity. This permutation group is abstractly known as the dihedral group of order 8. Group actions. In the above example of the symmetry group of a square, the permutations describe the movement of the vertices of the square induced by the group of symmetries. It is common to say that these group elements are acting on the set of vertices of the square. This idea can be made precise by formally defining a group action. Let G be a group and M a non-empty set. An action of G on M is a function f G times mm such that f equals x for all x in M element of the group G, and f equals f for all G, h in G and all x in M. This last condition can also be expressed as saying that the action induces a group homomorphism from G into Sim. Any such homomorphism is called the representation of G on M. For any permutation group, the action that sends G is called the natural action of G on M. This is the action that is assumed unless otherwise indicated. In the example of the symmetry group of the square, the group's action on the set of vertices is the natural action. However, this group also induces an action on the set of 4 triangles in the square, which are T1 equals 234, T2 equals 134, T3 equals 124 and T4 equals 123. It also acts on the 2 diagonals. D1 equals 13 and D2 equals 24. Kaylee's theorem. Any group G can act on itself in many ways. In particular, there is a regular action given by multiplication in the group. that is, f equals gx for all g and x in G. For each fixed g, the function fg equals gx is a bijection on G and therefore a permutation of the set G. Each element of G can be thought of as a permutation in this way, and so G is isomorphic to a permutation group. This is the content of Kaylee's theorem. Consider the group G1 acting on the set 1, 2, 3, 4 given above. Let the elements of this group be denoted by E, A, B and C equals AB equals bar. The action of G1 on itself described in Kaylee's theorem gives the following permutation representation. FAFBFC. Permutation isomorphic groups. If G and H are two permutation groups on sets X and Y with actions F1 and F2 respectively, then we say that G and H are permutation isomorphic if there exists a bijective map lambda XY and a group isomorphism psi GH such that lambda equals F2 lambda for all G and X in X. If X equals Y, this is equivalent to G and H being conjugate as subgroups of Sim. The special case where G equals H and psi as the identity map gives rise to the concept of equivalent actions of a group. In the example of the symmetries of a square given above, the natural action on the set 1, 2, 3, 4 is equivalent to the action on the triangles. The bijection lambda between the sets is given by it. The natural action of group G1 above and its action on itself are not equivalent, as the natural action has fixed points and the second action does not. History. The study of groups originally grew out of an understanding of permutation groups. Permutations had themselves been intensively studied by Lagrange in 1770 in his work on the algebraic solutions of polynomial equations. This subject flourished, and by the mid-19th century a well-developed theory of permutation groups existed, codified by Camille Jordan in his book Traité des substitutions et des equations algébriques of 1870. Jordan's book was, in turn, based on the papers that were left by Évariste Galois in 1832. When Kaylee introduced the concept of an abstract group, it was not immediately clear whether or not this was a larger collection of objects than the known permutation groups. Kaylee went on to prove that the two concepts were equivalent in Kaylee's theorem. Another classical text containing several chapters on permutation groups is Burnside's Theory of Groups of Finite Order of 1911. The first half of the 20th century was a fallow period in the study of group theory in general, but interest in permutation groups was revived in the 1950s by H. Wieland, whose German lecture notes were reprinted as finite permutation groups in 1964.